Hi, everybody. Welcome to our next round of Fellows Talks. Today we have Abdelrahman Elabd to talk about his project today. His mentor was Marcus Atkinson. Marcus, can you say a few words about Abdul's work?
Yeah. So Abdul's working on a project to convert PyTorch geometric graph neural network models into HLS, which we can then easily load onto firmware. This has been a needed project for us because we have a variety of different graph neural networks that are written in this PyG. And a lot of our approaches for actually implementing and putting them on FPGAs is done in HLS. And so Abdel has written us a nice little converter for some of the modules. I think that's about it. So
Great, thanks.
no
Whenever you're ready, Abdul.
Thanks for the intro. Yeah, so my name is Abdelrahman. My friends call me Abdel. I'm a graduating senior at University of Pennsylvania, and here to talk to you about my project, PyTorch Geometric HLS. PyTorch Geometric is a Python PyTorch extension for dealing with graph neural networks, which are basically just neural networks that train and predict on graph structured data. And I've been working under the mentorship of Marcus Atkinson, as well as Professor Neubauer at the University of Illinois as well, and Professor Javier Duarte at UC San Diego. And I've been working in collaboration with Fizal Razavi-Maleki, who's in the chat. He's a grad student at University of Illinois as well, at Urbana-Champaign. Here's the link right here at the bottom. This is the development branch. We're still in the process of making the pull request to integrate functionality with my converter with the overall HLS for ML toolkit, which I'll explain in a bit. But if you want some early VIP access, that's the link right there. So graphs. I'm going to start by talking about, just a quick overview of graphs and graph neural networks. We can represent a graph as a bunch of nodes and a bunch of edges. And basically, we can represent the nodes with a node matrix. Now, this is a matrix that has n rows, where n is the number of nodes in the graph. And let's say p columns, where each node is represented as a 1 by p vector, right? So, because there can be several attributes, we can represent each node as a vector. Likewise, each edge can be represented as a vector. So we can think of the edge matrix, this E right here, as having, let's say, m rows, where m is the number of edges in the graph, and let's say q columns, where each edge is represented as a 1 by q vector. And then the last thing we need to represent the graph is the edge index, which basically is an m, right? M is the number of edges, is an m by 2 matrix, right? So basically the first column of this edge index matrix defines the index of the receiver node for that edge. And then the second column defines the index of the sender node for that edge. Or it can be backwards, but it doesn't really matter. All you need is basically the 2 nodes that each edge connects. And so, yeah, when we train neural networks on this kind of data, we can do some really cool stuff. The main benefits of this is that we are efficient at encoding context, especially within physical, spatial, dynamic systems. They're generalizable. I'm going to go into that in a moment. They're also permutation invariant. also going to go into that. So what I mean by generalizable and contextual, so an n-body simulation is one of the most intuitive examples of this, and this is actually from a paper by DeepMind, which they wrote in 2020. And so basically what they did in this paper is they trained graph neural networks on different types of molecules, and then used these trained molecules to predict the physical simulation of the system, right? The next time step of the system. So for example, they would train a graph neural network on let's say these pink molecules right here, and then if they had a new initial configuration of these pink molecules, they could predict how those molecules would progress as time goes on. And the way they're generalizable is, for example, you might prove this, they could train graph neural networks on these pink molecules and then predict, for example, how these blue molecules would behave, even though the network had never been trained on those blue molecules. Or they could train it on the pink molecules and then predict how the blue molecules would interact with the black molecules. So they're very generalizable. Basically, these graph neural networks were not learning pink molecules behave in this way, the blue molecules behave in this way, and so on and so forth. It learned given such node attributes and such edge attributes. These are the latent computations that we need to do in order to efficiently predict how these molecules interact, how these particles interact. And what I mean by efficient at encoding context is that, for example, if you look at the top, these top graphs here, it's position of and the position and the relationship between any molecule and all the other molecules in this simulation is implicitly defined by that molecule's position within the overall graph. So these are two new benefits of graph neural networks, and they're also permutation invariant. So you can take as an example convolutional neural network, which is also really good at encoding context within systems. A convolutional neural network would not be permutation invariant. You can imagine if you fed these pixels to this convolutional neural network in a different order, the output of that convolutional neural network changed. Even if it was a well-trained CNN, imagine you flip this picture of a car upside down, right? If it was a well-trained CNN, it would still predict that that's a car. But in order for that to happen, you would need to have upside down training data when you trained the neural network. The main point is if you flip this car upside down and then fed it to the same neural network, the actual numerical final output would also change. It basically wouldn't think it's seeing the same exact picture, just flipped upside down. Whereas with a graph neural network, they are permutation invariant. So you can imagine if you're following my mouse here, if this was the first node in the node matrix, and this was the second node, if we switched the placing of these two, if we made this the first node in the node matrix and then this the second node in the node matrix, as long as you updated the edge index matrix to account for that change, then it sees the same exact graph. So that's what I mean by permutation invariant. It doesn't matter specifically the order that the graph is represented. And so this brings me to the accelerated tracking project at IRIS-HEP, which is, I'm sorry, I forgot to mention I'm a fellow at IRIS-HEP. So basically what IRIS-HEP uses graph networks for is particle tracking. That's what the project that I'm part of uses them for. Pictured here is the CERN detector at the Large Hadron Collider. And what happens in the middle here is these particles will collide, and then a whole bunch of particles will spray out. And as they spray out, they pass through these detector layers, right? And now every time a particle passes through a detector layer, that's a hit. We call that a hit, and we can represent that as a node within the graph. So yeah, for any event, it makes a whole bunch of hits, makes a whole bunch of nodes, and we can make a graph out of that. Basically, we start with a fully connected graph, where basically every node is connected to every other node, basically. And then we do some geometric cuts on the graph. So basically we set a maximum on the angle that any edge can take. So for example, if you started with a fully connected graph, it wouldn't make sense let me back up a bit. The point of this is we want to track particles, right? We want to see which hits are caused by the same particle. So of course, it wouldn't make sense for a particle, for a hit that was caused right here, to also be the same particle that caused a hit right here, right? So basically, we start with just a geometric cut. We say there's a maximum change in angle that an edge can have, realistically. And then after that, we use an interaction network, which is a type of graph neural network, to predict which of the remaining edges are true edges. And by true edges, I mean a true edge is an edge that connects two hits or two nodes which were caused by the same particle. And so once we find out which edges are true edges, we can kind of track the particle through space as it passes through all the detectors, and that gives us some clues as to what kind of particle it is. Oh yeah, so at this bottom right here, you can see kind of that interaction network. And so this brings me to HLS for ML. HLS for ML is a toolkit for converting Python neural networks to HLS, right? So that we could implement them on FPGAs. Now, we know at the Large Hadron Collider, it's being upgraded currently, and there's already really high data rates there. So basically, these tracking algorithms, we want them to be fast. So we have interaction networks in Python that do pretty well on simulated data. They get 99% accuracy, training on 1,000 events, something like that. And so we just want them to be faster, which is the purpose of my project. So HLS for ML does a pretty good job of converting neural networks to HLS, but it currently only has support for feed-forward neural networks, something like what's shown on the left here, right? Where it's basically a bunch of neural network layers, and the output of each layer is just the input of the next layer. So it's a feed-forward mechanism. Whereas with graph neural networks, we don't see this feed-forward data flow. So this is a schematic of the interaction network that we've been using. And these phi E blocks represent edge blocks, as in these are neural network blocks that make edge predictions. This phi N block represents a neural network that makes node predictions, right? So edge predictions is in the edges of the graph, and node predictions is in the nodes of the graph. So you can see this first edge block, right? It takes as input the node attributes, the edge attributes, and the edge index, and it outputs an updated, it's updated edge attribute predictions. And then you can see this node block takes the original node attributes, and it also takes these updated edge attributes from the phi E block. So right from the start, we see a non-feed-forward data flow. And then finally, this last edge block takes the updated node attributes from phi N, takes the updated edge attributes from phi E, and it takes the edge index. So yeah, it's non-feed forward. And also, each of these blocks may have more than one input. So that's basically the functionality that my project aims to mm, so this is HLS, right? My project PyG to HLS. This is HLS. The other half of that is PyG, also known as Torch Geometric, also known as PyTorch Geometric. This is the PyTorch extension for working with graph neural networks. And the main paradigm we're looking at is the message passing module. A lot of the other PyG modules inherit from this message passing module. And the thing it's really good at is it breaks down the message passing networks into three things, right? Which is message, aggregate, and update. So it sends messages, right? It constructs messages between the graph, right? Given the node attributes and given the edge attributes, it constructs some set of messages, and then it aggregates these messages. Again, in the permutation and variant aggregation. So permutation and variant aggregation, you can think of that as a sum, mean, max, min. It's an aggregation which doesn't matter on the order of the inputs that are given to it. It's sub factors. So it constructs these messages, and then for each node, it aggregates net messages around it, and then it uses these messages to update the state of the system. So what I did in my project is I basically constructed 3 new HLS layers for HLS for ML, which are edge block, node block, and aggregate. And there's also this graph block, but first we need to go over these. So this edge block, what it can do, yeah. So this edge block, what it can do, it can create messages, right? It take the node attributes, edge attributes, and the connectivity of the graph, i.e. the edge index, and it can create messages, or it can update the edge attributes, or it can aggregate, or it can do all three. So that's the edge block. The node block basically just updates node attributes. That's its functionality. And then there's also this aggregate. Now, because we want this to be fast, typically, wherever possible, we would want to do this aggregation within the edge block. But it's not always possible. For example, if your neural network has a node block as the first block, as opposed to an edge block as the first block, then there exists no pre-aggregated edge attributes for the node block to use, right? Because each node needs aggregate of all the messages being sent to it in order to predict that node update. So this aggregate class is for that scenario. And then so that brings me into this graph block, right? Which is the parent module for edge block and node block. Well, basically what this graph block does is it lies to HLS for ML, and it tells it that this edge block or this node block is a single layer, because that's kind of the format that HLS for ML expects. So each thing is just one network layer. This edge block and this node block may in fact be an entire neural network on its own. So graph block handles the line, right? And so using PyG to HLS, we've been able to convert the interaction network that we've been using. And these are just some ROC curves using different aggregation methods. So here you can see with the sum aggregation method using 10-bit precision, using 11-bit precision, mean aggregation method using 10 through 20-bit precision. You can see at about 18, 19 bits, you get more or less the same performance as the Torch model, as the pure Python graph neural network. And this is with max aggregation up top here. And so basically, what are the user inputs to PyG to HLS? Basically, you have to give it the model and the forward dictionary and the graph dimensions. Now, the forward dictionary is basically, you can see an example of this on the right. This is an example of our interaction network. Basically, you give it the name of the module. So if your torch module has, if self.r1 equals edge block, then you have to kind of define that in the dictionary because, otherwise we can't infer the forward function of the torch module, overall. So it's very simple. You give the name of the block and whether it's an edge block or a node block, and you give it in order. That way, it'll be able to, create an identical HLS version of that. And so that brings me to the problem of graph padding and graph truncation. When we implement these graph neural networks on an actual chip or on an FPGA, it's one and done, right? You implement it and then that's it, right? Now it's ready to receive input and do some inference. So it's a fixed size, and so when we feed it graph inputs, it's expecting a fixed size input. And so you either have to pad the graph if it's too small, or truncate the graph, like cut off some of the graph if it's too big. Now this can sometimes be good and it can sometimes not be good. So if it's truncation, it's always bad. You can imagine if this graph right here, if we have 3 too many nodes and we need to truncate 3 nodes, there's no way we can do that without losing some information. Right? There's a loss of information no matter how you spin it. The same thing if you're truncating edges. Right? If you have too many edges, can't do that without losing some information. Now, there are ways you can mitigate the amount of information lost. You can look for disconnected nodes, right? Like there's a node that's completely disconnected from the rest of the graph. And in the message passing schema, it's not going to share any information with the graph anyways. But that's computationally expensive. Again, the point is we don't want it to be computationally expensive. And so that comes to padding. Now, padding, again, can sometimes be good. It can sometimes be bad. You can imagine one scenario in which it can be good is, let's say we need 2 more nodes and 1 more edge. This would be the simplest example, right? So we could construct 2 dummy nodes out here, right? Like 1 node here, 1 node there, and then construct them and then connect them, with the dummy edge. And so now we've created basically a bipartite graph, right? Where we have our dummy graph right here, which just consists of 2 nodes and a single edge, and it's completely disconnected from our actual graph. So when it comes time for message passing, there's no false information that's being introduced into our actual graph. And so inference will be more or less, it'll be actually exactly the same. But there are some cases in which padding is bad. Let's say, for example, you have just enough edges, right? You don't want more edges, you don't want less edges, but you don't have enough, well, actually, that would be a good example. If you have just enough edges, but you don't have enough nodes, you can just, again, construct the dummy nodes out here and leave them completely disconnected. However, if you have just enough nodes and not enough edges, then you can't add any nodes, but you need to construct some new edges. So the only possibility would be to construct edges between these true nodes, these actually existing nodes. And so when it comes time for message passing, there is going to be some false information that's being propagated. Now I've made a fixed graph size function, which I still haven't included in PyG to HLS, but I'm going to. And basically what it does is it fixes the graph size, right? It either performs this truncation or this padding, and it also returns a Boolean that tells you if it's a bad graph or if it's a good graph. Bad graph meaning, right, either there's truncation or there's padding, which introduces false information into the graph. If it's a good graph, right, then it's either a graph that was just the right size, or a graph where we created some dummy nodes or dummy edges that were completely disconnected from our actual graph. And so here's some support yet to come. Nonlinear layers, convolutional layers, still haven't implemented those, and an arbitrary number of layers per block. So currently for each edge block or node block, we can have either anywhere from 1 to 4 layers. We can do more, but because the way C++ is, it's hard to define or initialize an arbitrary number of objects, because the backend is written in C++. So that's yet to come. And higher degree neighbors for the message and aggregation steps. So currently, right, messages are for each node. All its messages are constructed as an aggregate of all the edges it's immediately connected to, right? It's first degree edges, where you can imagine, somebody might want an aggregation that includes all the edges that this node is immediately connected to, and then all the edges that its neighboring nodes are connected to. So that would be like a second degree kind of thing. Likewise for constructing the messages in the first place, right? So right now, each edge's message is constructed using its receiver node and its sender node. But you can imagine some schema in which you want the receiver node and the neighbors of the receiver. You want the sender node, neighbors of the sender node, and you want that information in order to construct the message. There are ways to get around this, and that you can have more than one message passing step, right? So if you send messages once, that's first degree neighbors have shared information, then you can send it again, right? So now I've received information from my first degree neighbor, but in the prior message passing step, my neighbor has received information from all of his neighbors. So in this step, I've received messages from my neighbor's neighbors in a way. And the last thing is different messaging schemes. So currently, right, basically, in order to construct the neural network input that creates the messages, it's basically concatenating the receiver attributes, sender attributes, and the edge attributes. You can imagine different ways of for example, you could have, just a different order of this concatenation, or again, a higher degree of neighbors being included as the neural network input. And so, yeah, I just wanted to finish this off with one slide of shameless self-promotion. If you guys have any more questions about my specific research, or if your PhD program could do with a strapping young lad like myself, please feel free to contact me. Yeah.
So thank you, Abdul. Any questions?
I had one on the slide about rock curves, which I think is not the focus of your work, but in particular in the middle plot, I was struck by how quickly reducing precision when created a random number generator out of the algorithm. But I realize I don't know what it's the precision of, which probably answers my question, but do you have a feeling for why that's so sensitive?
Yeah, so first of all, yeah, I should explain what the precision is. The precision is basically like, because, we're implementing these on FPGAs or just high-level synthesis, so we can no longer use floating point precision. We use fixed point precision, which basically means, so this precision right here is just the number of bits we use to represent any number, right? So we use 10 bits to represent a fixed point number, integer number, or 11 bits, so on. Now, yeah. So decreasing the amount of bits basically it decreases the maximum positive number, minimum negative number that can be represented in that precision. So basically, what you're seeing here is we're getting a ton of overflow error. So we were tracing the intermediate products of graph neural networks that we were testing as we were making this, and we saw a lot of overflow once the bits became low enough. So, for example, if one layer of -80, that would overflow and come around to, I think, +30. So it completely changed the activation. And when you get enough of those overflows, it basically does become a random generator.
Okay, thanks. I misunderstood how the bits worked. It's reducing the precision reduces the min and max, not the precision of a number represented. Okay, thanks. That makes sense then.
Okay, any other questions? All right, well, thank you for the presentation. Thank you, Marcus, for your mentorship. Thank you, everybody, for attending. That's it. That's all we have for today. So there'll be some more coming up probably next month. So thank you.
Thank you guys for watching.
Well, thank you.
Yes. Thank you.
Thanks. Bye.